So Duncan, take it away.
All right, so today I'm presenting my paper, Uncertainty-Aware Multitask Allocation for Parallelized Mobile Edge Learning, or UMMAP-MEL. And some context on this paper are that it's the latter half of my thesis, which my supervisor, Sarah El Sayed, condensed into 6 pages and submitted to GlobCom as a conference paper. GlobCom is the global conference on communication, and it is running presently this week in Kuala Lumpur, Malaysia. Sarah and a bunch of other people from the TRL, Telecommunications Research Lab, including Maria, are there right now presenting this work, and it'll be published soon, so you can look it up on arXiv and cite me. A high-level overview of this paper is that it's about a data allocation scheme for training multiple neural networks in parallel. And workers in this scheme have heterogeneous characteristics. So the workers have different capabilities from one another, and their capabilities are uncertain and change over the duration of the training regime. While this problem is not identical to scheduling in DCP, there are some really similar challenges, including this uncertainty, and some useful insights, I think. Now, parallel learning consists of an orchestrator which recruits several distributed workers that it hopes to use to train neural networks in parallel. And it proceeds in cycles of the following 3 steps. First, an orchestrator sends parameters and training data to workers. The workers will then train those parameters on that data and then upload the resulting parameters back to the orchestrator, which will then aggregate all those parameters into a single parameter set and repeat the process to continually improve the performance of the neural net. And these worker devices are heterogeneous edge devices like desktops, phones, tablets, and even spare server resources. And because they have differing capabilities, we need a way to adjust the size of the task that gets given to them so that we're not limited by the weakest worker in the cluster. In this research, I've been doing that by varying the amount of data that each worker receives. So workers will receive an amount of data that's proportional to their training capability. A challenge here is that workers are user-owned edge devices, and so they'll be used for other things during the duration of the training routine. And these tasks will cause resource contention with the training process, and this is going to alter the capabilities of the worker. We're going to model this variation as uncertainty. And so worker capabilities will stochastically follow some probability distribution during the training routine. The orchestrator wants to train its neural networks as fast as possible given the resources available, but it's not critical that all data samples that get allocated get trained on. And so for each one of those cycles of 3 steps, the orchestrator will impose a deadline. And if a worker trains past this deadline, it'll forget about the samples that it hasn't covered yet and will upload its partially trained parameters anyway. Another thing to consider here is that the orchestrator is doing this for multiple tasks at once. And each of these tasks has its own neural architecture, data set, deadline, and loss function. But each worker can only train on one task at a time. I'm going to take a moment and contrast this with scheduling in DCP. In both settings, an orchestrator has to allocate some number of slices from multiple tasks to a set of distributed workers. And the delay of these workers is proportional to the amount of data or slices that are allocated to them. And these workers have heterogeneous and uncertain capabilities that change during the duration of the job. Some differences with DCP are that the orchestrator seeks to minimize training time while the scheduler only wants to maximize profit. And parallel learning has this deadline property. If a worker doesn't complete its task on time, it'll upload the unfinished result anyway, regardless of the data samples that it missed. To do this, I've used the Gurobi optimization framework to calculate how much data to allocate to each worker in order to minimize the sum of the runtime of each task. And to use this, we need to model the delay of a parallel learning job. So the delay of a parallel process is the same as the delay of the longest running subprocess, assuming all the subprocesses start at the same time. In the parallel learning context, that means the orchestrator can only move on to the next cycle when the last worker returns parameters from the previous training cycle. And so what we want to do here is to minimize the maximal delay of each worker associated with each job. That's encapsulated in this equation, where W is the set of workers associated with a job, DI is the amount of data allocated to the worker, and CI is the training capability of the worker. This figure, MD, represents the delay of a parallel learning job as calculated by our model. But this doesn't factor in uncertainty. We can't calculate a single figure for the delay because that depends on capabilities, and the worker's capabilities are uncertain and vary over time. And so what we need to do is take an expected value over the probability distribution of worker capabilities. This equation here represents that. And one of the problems with it are that we would need to integrate over every worker capability distribution simultaneously in order to calculate this. That's too expensive. It's not practical to do this for a cluster of any meaningful size. And so what we've done is consider the maximum expected delay. And there's a subtle difference between the max expected delay and the expected max delay. But one of the differences is that it's less expensive to calculate, since we only need to do this expected value calculation over a single worker's capability distribution at a time. And so this is the objective that we're going to minimize with Gurobi. Like I said, I've used the Gurobi optimization framework to minimize the MED objective by allocating differing amounts of data to each worker associated with a job. The experimental setup I used was a cluster of 10 Jetson Nanos that were connected over Ethernet. And that's a picture of the actual cluster sitting on my desk, however many months ago. And to simulate these workers being accessed by other programs, we're going to run stressor functions in a separate thread. These stressor functions are designed to place load on specific system resources, and that will cause contention with the training process and alter the worker's capabilities. Workers will have 3 states, each corresponding to a specific stressor function. In the idle state, this represents the worker not being used for anything except the training task, and so there's no stressor function. In the training state, the stressor function does matrix multiplication continually in a separate thread, which places load on the GPU and slows down the worker's training. Whereas in the downloading state, the stressor function will download data continually to place load on the network link. At the beginning of each experiment, the state distribution of each worker will be randomly set. So the random distribution is itself randomly set. And since workers' PDFs are set randomly, the workers will have differing average training capability. And so even though all the workers have the same hardware, because they're running these stressor functions, their capabilities will be different, and we can have heterogeneity with uncertainty. I ran all these experiments using my own framework, the Axon RPC framework, and you can find the code for these experiments on my GitHub page at multi-orchestrator PL. The training tasks I used all came from the MNIST Foundation. MNIST isn't just one data set. They also have a fashion data set where neural networks are trained to recognize images of clothing alongside a data set of handwritten digits. And I used different architectures for each task. So the MNIST FFN task, I used a feed-forward network with 60 shards of data. So that's 30,000 MNIST samples because a shard is 500 samples. I also trained a CNN on the handwritten digit data set and a CNN on the fashion image data set. And note the deadline. Deadline is important. I tracked success with two metrics. The first one being the training time, which is the time for a single training loop averaged across all tasks over the duration of the experiment. And I also recorded the data drop rate, which is the percentage of data samples that weren't trained on because the worker hit the deadline and couldn't finish the task that was allocated to it. I also implemented two baselines. The first baseline I called MMTT ideal, that's minimize the maximum training time. In this scheme, the orchestrator is aware of the states of each worker at the beginning of each update cycle, and it can reallocate data in between cycles to remain optimal as the states change. This is the ideal case. This is the maximum expected performance given the resources available and the time available. So we're expecting MMTT ideal to outperform our MED objective. The second baseline is a uncertainty naive approach. So in the scheme, it's as if the orchestrator benchmarked workers once and didn't take into account their varying capabilities. And it assumes the workers' capabilities stay the same during the whole training routine. And so we're expecting MMTT uncertain to underperform MED. I ran two sets of experiments. The first one, I varied the number of workers from 4 to 10, and I used all three of the tasks that I reviewed. And then the second set of experiments, I varied the number of tasks from 1 to 4. I used all 10 workers, and to keep the measuring scale even, I used duplicates of the same task when I increased the number of tasks, because if I used differing tasks, the different tasks place different load on the system, and that wouldn't be an even measuring stick. So here's the results of training time versus the number of workers. And the number of workers increases as you move right along the graph. So the training time decreases because the load on the cluster is the same, but with more workers, that's less load per worker. And each of the three schemes are represented by a different colored bar. So the ideal scheme that can perfectly allocate data is the blue bar. And you'll notice that's the lowest out of all of them, which is the result that we were expecting. MED, which is the orange bar, falls in between MMTT and MMTT uncertain at high numbers of learners, but at low numbers of learners, it seems to get roughly the same training time. In terms of data dropped, the R scheme, MED, consistently performs around halfway between MMTT ideal and MMTT uncertain. So it loses only around half of the data samples that the uncertainty naive approach loses. When varying the number of tasks, we can see that while training time rises with the number of tasks for all schemes, that rise is capped at the deadline. Because workers can't work past the deadline, the training time can only be as high as the deadline. And as well, we see the same performance pattern that we were expecting, where MMTT ideal outperforms MED, which in turn outperforms MED uncertain or MMTT uncertain. We see a similar pattern in data drop rate as we vary the number of tasks as we saw when we varied the number of learners. MED seems to perform in between MMTT ideal and MMTT uncertain. Now, you might be wondering why with 3 tasks and 10 workers, the data drop rate is different than in the experiments where we varied the number of learners. That's because I've set the deadline lower for this task. Now, an analysis of the training time figures is that the training time increases as the load per worker increase, but that increase is capped by the deadline. And so there are tighter gaps when the load is higher because more workers hit the deadline. Better scheduling routines only show better training time in low load circumstances where not very many workers hit the deadline and training jobs can actually be reduced by better data allocation. We saw better results with data drop rate. MED is consistently about halfway in between MMTT ideal and MMTT uncertain. And so you can expect at most a 50% reduction in data dropped by using an uncertainty aware approach that calculates the expected value. And so in conclusion, you can mitigate uncertainty when scheduling parallel learning jobs by reducing the maximal expected delay of each worker associated with each job. And doing this will earn you at most about a 50% reduction in dropped data samples as compared to an uncertainty naive scheme. While there are some benefits to speed, this only shows up when not very many workers hit the deadline. Because if the cluster load is high enough that workers hit the deadline, then each job is only going to take the same amount of time, regardless of how the data is allocated. That's the end of my presentation. Thank you for listening to me today. Are there any questions?
Thank you very much. Excellent presentation. I'll give people a chance to ask questions, and I have a few of my own if people don't have theirs ready.
Does ChatGPT have any questions?
Brian's got to ask it real quick. I guess was Ryan or Will doing it? I don't remember who was asking ChatGPT earlier.
I had asked, but I have ChatGPT closed now, so it's too much.
That's fair. So no ChatGPT questions. Okay, well, I'll kick things off then, because I do have a couple questions. You answered yet again, and this is often the case with presentations. People answer some of the questions that I have before they get to the end. But I was curious to what degree overscheduling can help with the maximum delay issue. That whether when you let's say you want to run. And this is something maybe I wasn't entirely clear on, is let's say you want to run batch sizes of 10 for the training purposes, because my understanding is that you're sending it out, each one is training their own or running their own training on a few samples, and then you send it back and aggregate the gradients so that you can have the overall change in the main model. Is that correct?
Yeah.
Okay. And it sounded like the amount of returned results is going to vary depending on how many return the data within the delay. Is that also correct?
I'm not sure, but so to be clear, I'll explain what it is. Yeah. The orchestrator always gets the same number of parameter updates in each cycle because all workers upload a parameter update. And it always receives that as late as the deadline. And some of these parameter updates haven't been trained on all the data that was allocated to them.
Oh, so you get back whatever they've done in the time that they had available. So so you gave each of them 100 samples, some of them ran 80 samples, some of them ran 15 samples, and each of them sends their gradient update.
Yeah, because it's not the end of the world if some of them miss some samples.
And that makes a lot of sense. I don't know if I'm sure this doesn't relate as much to your thing. I'm curious whether it's how they weight it, if they just do like a direct weighting based on the number of samples returned, or what the approach is for that stuff. But I assume it's probably something relatively simple like that.
When you say weighting, do you mean like in a weighted averaging or like weighting on the workers?
Oh no, weighted averaging term.
Yeah, it is weighted based on the number of samples that were trained on, not the number of samples that were allocated.
Okay, perfect. And that makes a ton of sense. So I guess I was curious with regard to as you change the number of workers, and if you perhaps try and say, let's say you over allocate. So let's say we want to do, 10. We want to have 10 workers running these things. If you up the number of workers to 20, but you only accept the 10 results that had, say, the most updates, is there necessarily any benefit to doing that kind of thing? I don't know if that's the kind of thing that you saw in the literature. I know that wasn't directly part of your research. And I can clarify if my question doesn't make sense. I know it's a little bit in the weeds.
It is in the weeds, and there's diminishing returns to accepting updates. Like the network that results from aggregating 20 updates from workers wouldn't be that much better than the network that results from aggregating 10 updates from each worker.
Oh, see, I wouldn't have guessed that. I didn't realize that the diminishing returns started up so quickly with that kind of thing.
Yeah, so there are schemes that like the first 10 workers that return get aggregated and then it moves on to the next cycle and then it just ignores the updates from the last one.
Yeah,
That is the thing that gets done.
that makes sense. I imagine that is to kind of provide safer guarantees on the amount of data that's returned. So you're saying, okay, well, we're guaranteeing ourselves that we have a certain that we want to hit exactly this many. You're keeping a stability to the number of training samples that are used at each step.
Yeah.
And you're not getting updates from ones that only did 10 or 15 out of 100. But I can see why that might not be the thing you want to do if you want to guarantee time rather than you guaranteeing batch size. Josh asks, mentions that he's never heard of Gurobi, I think it was, until today, and asked if you can quickly explain what it is and why you chose to use it.
Sure. So Gurobi is an optimization framework that lets you solve systems of stuff, and you have to represent those systems in Gurobi's language. So in Gurobi, you can place constraints and so you define a bunch of variables to represent your system. You place constraints on those variables, and then you state an objective that you want to either maximize or minimize. And among the variables, you've told Gurobi which ones it's allowed to vary, and it will vary those variables to maximize or minimize your objective. And then there you go. So in this case, the variables that Gurobi was optimizing over was the amount of data that's allocated to each worker, as well as the associations between workers and tasks. And its objective function was to minimize the maximal expected delay.
Okay, so it's kind of like Google OR tools.
Yeah. I mean, I've never used Google OR tools, but I think
they
Google
just
OR
call it
tools
OR
is a
tools.
scheduler. So
yeah, OR tools is a generalized optimization framework, which sounds similar to what Gurobi is. In that, like, you set up your systems of equations and then it can perform either integer or in some cases discrete a continuous optimization. I think OR tools is primarily a discrete optimization, which Gurobi might be as well. I'm not sure.
I think Gurobi does continuous.
That's fair. Yeah, I guess in this case it was discrete, but if it can do continuous as well, that's useful to know about because that's the kind of tool that we always might make use of in various spots. I had another question with regard to the because you set up the kind of environment with the various workers transitioning between different stressor and non-stressor states based on probability distributions. I'm curious whether those were things that you came up with for the experimental conditions, or whether those were based on any sort of real world data for the kind of load changes that we'd see in, for example, a cell phone network environment where you have a bunch of cell phones connected together.
So the distribution of worker capabilities was not set from data that was gathered from real devices, but was controlled to manipulate results. Like, I spent a lot of time on this paper adjusting the heat of that distribution to give uncertainty-aware schemes a better advantage versus uncertainty-naive schemes. So that's a good question. Like, the distribution of the capabilities of the worker has a big impact on the performance of these schemes.
That makes sense.
And more uncertainty in worker capabilities mean larger gaps between the schemes, basically.
Okay, and I imagine, frankly, when I think about real world network availability and usage, and in an example like running it on a network of cell phones, I imagine worker availability to be quite variable. So that's something that might be interesting to look into at some point. I mean, I know you're done the paper, but that'd be an interesting topic to look at the real world availability of these things and see how well that reflects the kind of experiences that you've had with this, because that could be relevant for things like distributed training regimes on DCP. If we're trying to design something like that, knowing what the actual distributions are on the edge devices we have access to would be very, very useful.
Mm-hmm.
Also, I meant to mention, you mentioned that you had a GitHub link to, or you had a GitHub account or page for this project. Would you mind sharing the GitHub link if you haven't already in the book club channel
Sure.
at some point?
In the book club channel, yeah.
Yeah, that'd be wonderful. Thank you.
There it is. Just my name and then multi-orchestrator PL.
Awesome. Would you mind pasting that just in the book club channel for afterwards, just in
Yeah.
case?
Yeah,
That'd be awesome. Yeah, you don't have to do it right now, just whenever is convenient. Awesome. Yeah, so those are my main questions because the other ones, like I said, you already answered throughout the presentation. Did anyone else have anything they wanted to ask about this? Josh also asks, you mentioned using 10 Jetson Nanos. Had you considered using a variety of hardware? That's an interesting kind of thing you could do as well. Thoughts?
So it sounds weird to say that you want all the workers to be the same when you're studying this kind of thing, because an important thing when you're doing this is to have heterogeneity between the workers. But I guess if all the workers are the same, that lets you control the heterogeneity in the workers. Like if the heterogeneity was a result, like if I don't know, say I had a Raspberry Pi in that cluster, that Raspberry Pi would like have a different capabilities distribution, but it would also need different like stressor functions, because the matrix multiplication that would slightly load a Jetson Nano would completely fry a Raspberry Pi. Like if it was multiplying a 500 by 500 matrix on the Nano, it would still be able to do some training, while the Raspberry Pi would be a brick because of that. So it makes things much simpler to just have the same, like have the nodes in the cluster be the same.
And I suppose one other thing I might, if I you don't mind me adding something onto that, is that in the real world, I would imagine that the loads that are happening in the uncertainty that's happening on devices that are attached to a network like this probably are scaled appropriately to the devices themselves. So although you may have one device that's has a lot of capability and another device that has very low capabilities, the amount that's taken on by those devices by their kind of native applications that are running on them or native loads, those kinds of things are probably scaled similarly. It doesn't fully account for that because there's a difference in what that availability changes. So if 50% change in the availability of a Raspberry Pi, as you say, is very different from a 50% change in availability of a Nano versus 50% change in availability from an iPhone. But all of those things are still they probably have somewhat similar load distributions, or maybe not. I don't know. Interesting thoughts.
Yeah, I think a friend of mine named Ruslan actually studies, like, I think he's done some work into recording the like load distributions of user devices. So he'd be a good person to ask about this.
Yeah, that seems like the kind of thing that definitely, as we develop distributed training systems, which I know are very valuable to DCP, as we try and migrate things like that over to DCP, these are the kind of things we'll want to think about, and we'll want to think about the kinds of devices that end up being connected to the distributed compute network. Yeah, but always more experimentation to be done. That's the beauty of it. No matter how many questions you ask, there are dozens of questions that you haven't.
Yep. Doesn't stop.
Never stops. Science. Yes. Any other questions that people had about anything? There we go. Seems like we're probably good. Well, thank you very, very much for your presentation. We'll maybe end off a little bit early today, but that was excellent, and it's really cool to see some of the stuff that you were working on and some of the stuff that you'd be presented that would be submitted to these conferences, especially when it's so relevant to the kind of work that we do here. So thank you very much, Duncan. We really appreciate it.
Of course. Thanks for listening.
Everybody, have yourself a wonderful day. We'll see whether we have another book club by the end of the year. We may or may not, depending on availability and days that things fall on. But I will keep people updated. Looking forward to seeing you all the next time regardless.
Bye.
Cool. All
And
right,
bye.
thanks for the presentation, Dan.
Thanks, Duncan.
We were all thinking Duncan in parallel.
What's up, Yarn?